All right, welcome to Chapter 2 in your book. We're going to start by dealing with some constants that we're going to be working with through the entire year that we're together. And this one's called length, mass, and time, and it is, guess what it's going to deal with, length, mass, and time. And we're going to talk about many of the staples that we're going to be using, a lot of the constants that are going to be used in everyday problems. Objectives are going to be how to record data using scientific notation and record data using the SI units that we need to know. All right, here's the assessments. We'll come to these questions again, and hopefully by the end of this you can answer these questions. Express the following numbers in scientific notation. So by the end of this, you should be able to write all four of these numbers in the correct scientific notation. Another one, which of the following data are recorded using SI units? Which ones are SI units and which ones are not? By the end of this, you should be able to answer. Okay, here are our physics terms. Measurement, matter, mass, length, surface area, volume, and density. These are the main ones we're going to be talking about in this chapter, or in this part of the chapter. Also, scale, microscopic, macroscopic, temperature, scientific notation, and exponent. Here is the first equation that you guys are learning in the class. It's going to be the density equation. If you took chemistry or IPC, there's a good chance you already used the density equation. And we'll talk more about that while we learn the chapter. All right. SI units. These are pretty much the standard units we use for science, and we use the metric system a lot of the times. Physicists commonly use the international system to measure and describe the world. The system consists of 7 fundamental quantities and their metric units. The foremost, the ones we use over here, are mass, length, and time. The 3 fundamental quantities, like I said, are mass, length, and time, and they are used in just about every type of problem that we're going to be working. Mass describes the quantity of matter. Language, the store had a massive blowout sale this weekend. How is the term massive incorrectly used in the physics sense? Why is it incorrect? Can you suggest more correct words? Okay, so having a massive sale is not the same as a mass in physics terms or science terms. What do you think would be the right way to use it? Length describes the quantity of space, such as width, height, or distance. How long are you going to be in the bathroom? How might the word long be misinterpreted in the physics sense? Is the speaker talking about length? Can you suggest more correct words? So here we're talking about long is as in a period of time, not as in a length. So we have a problem there. And time describes the flow of the universe from past through the present into the future. In physics, this will usually mean a quantity of time in seconds, such as 35 seconds. Our base unit for time is going to be seconds, but there are going to be times when we can use other units. And I'll explain those along the way as we go. What time is it? How is the meaning of time, and what time is it different from the meaning of time, and how many seconds does it take to get across the room? So these are 2 different interpretations of time, and we need to make sure that we stay with the scientific term for this. Each of these 3 fundamental quantities has its own SI unit. Think, what are the SI units for these 3 quantities? Can you guess what any of the 4 fundamental quantities are? All right, here's the chart with all of our stuff. This is the fundamental units and physical quantities for the SI units. Mass is in meters. Basically, it's going to be in kilograms, which is kg. Length, we have several. It's going to be x, d, or l. It's measured in meters, which is a little m. Time is a small t. Its base is a second, a little s. Electric current is a capital I. In ampere, and it's a capital A. Temperature, capital T. Fundamentals, Kelvin, but we're going to be doing a lot in Celsius also. It's a capital K. Luminous intensity, that's IV. It's a candela, which is a little CD. And the amount of a substance, N, which is moles, or MOL. And hopefully you dealt with that in either IPC or chemistry. Okay, all matter has mass and takes up space. I'm hoping you've heard that before. A solid rock is matter, but so is gas, and liquid is also. But all of these have mass. It has particles that make it up. With your hand out of the window in a moving car, you feel in the air pushing against your hand. So you know that air has to have mass because it's pushing back against you. Mass is an intrinsic property that measures the quantity of matter in an object. Your mass does not change if you go into space. So your person, your body, has the same amount of mass no matter where you go. That does not change. That makes it an intrinsic property. Weight is an extrinsic property that depends on the gravity force acting on you. Your weight does change if you go into space. So you weigh different here on Earth than you weigh into space. Your mass is the same both places, but your weight would be different. Objects with more mass are more difficult to speed up or slow down. This property of mass is called inertia. Inertia is basically the reluctance of an object to change its state of motion. Reluctance of an object to change its state of motion. These two balls are the same size. Which one would be easier to throw? 10 kilograms or 0.2 kilograms? I hope it's obvious. 0.2 kilograms. Can anyone describe the concept of inertia without using the word itself? Think about making things move. Think about making things stop. Think about making things change direction. Like I said, helping you out here, it's the reluctance of an object to change its state of motion. To fully describe a quantity like mass, you must provide a value and a unit. This object has a mass of 2 kilograms. The value is 2, the unit is kilograms. So you have the value and the unit. In the SI system, mass has units of grams and kilograms. 1 kilogram is 1,000 grams. So 1 dime is equal to 1 gram. 2 nickels would be 10 grams. We have like steel sitting on here as 1 kilogram, which is basically 1 kilogram is the same as 2.2 pounds. A rock could be 1 kilogram. We could have 1 kilogram of water, 1 kilogram of air. All right, length is a fundamental quantity. There are 2 common systems of length units you should know. The English system uses inches, feet, and yards. That's what we use here in the United States, and it's very, very confusing to use. The metric system, using millimeters, centimeters, meters, and kilometers, is much easier to use because you're just basically moving the decimal going by powers of 10. The meter is the SI base unit for length, and we will be using this all year long. Time is a fundamental quantity. The SI unit for time is the second. Just about any answer that you're going to give me is going to be in seconds, and I will tell you when you don't use seconds. So a millisecond is 0.001 seconds, 1 minute is 60 seconds, an hour is 3,600 seconds, and so on and so forth. And we'll be doing a lot of little conversions to figure these out later. Working with mixed units. Before calculating, you should always convert values into a single unit. So here you have the time of 2 hours, 20 minutes, 9.2 seconds. So if I'm going to take everything into seconds, they said 2 hours basically is 7,200 seconds, 20 minutes is 1,200 seconds, and then we had 9.2 seconds. Add them all up, you get 8,409.2 seconds. So basically this is the oops, that's moving around there. Let's do this. This is for 2, this is for 20, and then this is our 9.2 seconds. So you add them all up, they're all in the same unit. Physical objects and measured quantities have vast variations in size. If you look here, you've got the nucleus, which is very, very small, 10 to the negative 15th. Atoms are not quite as small at 10 to the negative 5th. Bacteria is 10 to the negative 5th. A human is about 1 meter tall. That's actually kind of small for a human. It's probably a kid. Separation of cities, you can have 10 to the 5th meters. Interdisciplinary distances, 10 to the 10th. And then you have the Earth to the Sun distances, 10 to the 15th. All these can be represented with a power of 10. Macroscopic scales. The macroscopic scale includes the scale of ordinary life. Doing work on the macroscopic scale. Here, we haven't talked about forces yet, but this person is applying a force to an object and rolling it a distance up the hill. Or down the hill. We don't know which direction it's going. Where microscopic scale is much smaller. Atoms and molecules make up matter on the microscopic scale. Can you see the difference? Macro is the very large. Micro is the very small. All right, scientific notation. You're going to get a lot of numbers in scientific notation, and you're going to have to be able to learn how to use them. Scientific notation is a system that makes it easy to work with the huge range of numbers needed to describe the physical world. Here we have 4.3 times 10 to the third. Even very large or very small numbers can be simply expressed as a coefficient multiplied by a power of 10. This right here, 4.3, is my coefficient, times 10 to the third is my power of 10. All right, scientific notation is a system that makes it easy to work with the huge numbers. The coefficient 4.3 has to be between 1 and 10. This first number right here will be between 1 and 9. Will be between 1 and 9, and then you'll have your decimal point, and then whatever numbers come after that. Powers of 10 are just that. 10, 102 equals 100. 103 equals 1,000. 104 equals 10,000. Those should be powers. 10 to the 0, 10 to the third. That should be. This is kind of confusing. We'll go over more of this in class. So basically, you're going to have 10 to the fourth, or 10 to the fifth, and so on and so forth. All right, for numbers less than 1, scientific notation uses negative exponents. The number here is 0.0015. So I have my first number here is 1.5, and then I have 10 to the negative third. So if I have 0.0015, and I want to write it in scientific notation, this is going to move 1, 2, 3 spots. That's what gave me the 1.5. Or it took 1.5 and divided by 1,000 like they did right here. But since I moved 3 spots times 10 to the 3 spots, that's where this comes in, negative third. Since we know it's very small, it's a negative number, since we were moving the decimal point to the right. Here is a chart for you showing you giga, mega, kilo, deca, deci, centi, milli, micro, and nano. These are the main ones we're going to use. We're going to use from giga, mega, kilo, deca, deci, centi, milli, micro, and nano. The other ones that they have in here, we're not going to use those. We usually, basically, the ones that I circled are the ones we're going to be using this year. Calculators and computers use the symbol E or EE for powers of 10. This is very important for you when using your calculator. The letter E stands for exponential, another term for scientific notation. You can think of that E as a times 10 to the button on your calculator. If you look at this, we have to enter 6.5 times 10 to the 9th. You press 6.5 in the EE button. A lot of times it's the second function of the button above the 7. So you'll have your 7 button here. Above that button, the second function is EE. And that's your exponent or EE button. So 6.5 times 10 to the 9th. It will look like this in your calculator. Okay? If we have 2.6 times 10 to the negative 5, we'd enter 2.6 EE, then negative, where's your plus and minus button. It's usually down by your 0, and then 5, and it'll look like this in your calculator. 2.6 e to the negative 5. If you look on page 49 in your ebook, there's a calculator button there, and this is going to give you practice to run through some of these problems, and it'll explain and help you work with scientific notation. Also, if you have your own calculator, it works well that way too. Use the calculator to write in scientific notation 4,180 joules. So 4180, we want to put that into scientific notation. Try it out and let's see what you get. So 4.18, because the first 3 digits there, you got 4.18. This first 4 is between 1 and 9, then you put your decimal and put the 1/8. Times 10 to the, that should be 10 to the third, that should be up. Joules, so you have 4.18 times 10 to the third. Because basically you had your decimal and 1, 2, 3. Now let's try 0.035 meters. .035 meters. How would you write that? Or put that in your calculator? All right, it'd be 3.5 times 10 to the negative 2. So you'd type 3.5. Then you'd go second function e, where you'd have the e, and then negative 2, just like they have over here. It'll say e or ee on your screen. So it should work easily that way. All quantities in physics are either fundamental quantities or derived quantities. Mass, length, and time are fundamental quantities. They're not derived from something else. Speed is a derived quantity that is calculated from other fundamental quantities. Think, speed is derived from what two fundamental quantities? What do you think makes up speed? Can you think of any other derived quantities? All right, dimensions for derived quantities. The dimension of a quantity is the combination of fundamental quantities that make it up. An example, we were talking about speed. Speed, the dimension is length and time. Length divided by time to be specific. So if I say 8 meters per second, because length is in meters and time is in seconds, that gives me a unit or a derived unit of meters per second. Density is mass per length. That should be cubed, so that 3 should be actually up here. Mass per length cubed. So you have all this information. Mass, what is the unit for mass? Kilograms per length meter cubed. Area is a derived quantity based on length. Surface area describes how many square units it takes to cover a surface. Surface area of 9 square meters. So we have 3 going this way and 3 going this way. So area is basically length times width. So 3 meters times 3 meters, giving me 9 meters squared. So the unit for area is meters squared. And this is probably going to work this right after I did this. Now this cube is a little bit different. It's got 3 meters on each side, but it's looking for the surface area of all 6 sides instead. How much would the surface area of this be? Question mark. And the last one, we have surface area of a sphere. That's 3 meters in length. So there's another formula that goes for this. I'm not really worried about you figuring out this. I'm just wanting you to know that it's got the same, it would have the same units. All right. Volume is another derived quantity based on length. It measures the amount of space in units of length cubed. So we have several things here. We have basically boxes, we have spheres, we have cylinders, we have cones, and all these we have surface area formulas and volume formulas. I will always and forever give you the formulas on quizzes and tests and anything like that. You do not have to memorize formulas. You just have to be able to recognize them. Density is an example of a derived quantity. It measures the concentration of mass in an object's volume. Steel has a density of 7,800 kilograms per cubic meter. Air has 1 kilogram per cubic meter. When calculating derived quantities, it would be important to use consistent SI units. P, well, this is not really P, but we'll talk about what that is in class more. Density. Mass is in kilograms, volume is in meters cubed, so you get kilograms per meters cubed. If density in kilograms per cubic meter is desired, then the mass must be in kilograms and the volume must be in cubic meters. All right, on page 47, you can use the calculator again, or you can use your own calculator if you want to answer the questions as we go along. All right, use the density calculator to answer this question. A delivered package has a mass of 2,700 kilograms and a volume of 35 cubic meters. What is the density? Well, to look at this, you can plug it in. It's got the conversion thing in your online book, or you can use your calculator. If you look, our density here is our mass divided by our volume. So 27,000 divided by 35 gives us 77 kilograms per meters cubed. All right, back to our assessments. Express the following numbers in scientific notation. So, get a piece of paper or something like that and write these out and see if you get them correctly. Go ahead and pause the video right here because I'm going to go on. Pause the video. 275 would be 2.75 times 10 to the second. That should be a superscript. I'm sorry, these aren't writing in superscript. 0.00173 is 1.73 times 10 to the negative third. That should be a superscript. 93,422, 9.3422 times 10 to the fourth. That should be a superscript. And then 0.000018 is 1.8 times 10 to the negative fifth, because this moved over 1, 2, 3, 4, 5 spots. Which of the following data are recorded using the SI units? Which ones of these are SI units and which ones are not? All right, so we talked about meters a lot. Meters is an SI unit. Inches are not. Pounds are not. Kilograms are, and seconds are. Those three are your SI units.